Welcome to all. Myself, Dr. T. Sasikala, Associate Professor and Head, Department of Chemistry, Sri Ramakrishna College of Arts and Science, Coimbatore. In this presentation, we'll discuss about Debye Huckle Onsager theory of strong electrolytes. In 1923, Debye and Huckle, and in the year 1926, Onsager put forward the modern theory of strong electrolytes. According to this theory, strong electrolytes which exist as ions in solid state must be completely ionized in solution at all concentrations. If the solvent has a high dielectric constant or if the solution is dilute, the forces of attraction between the oppositely charged ions will be very small. Therefore, the ions will lie apart from one another. On the other hand, if the solvent has a high dielectric constant or if the solution is dilute, the forces of attraction between the oppositely charged ions will be very small. In this case, the ion will also lie apart from one another. So in this condition, the ions will not separate and remain in pairs as A plus B minus, known as ionic doublets. Hence, the electrolyte is completely ionized, but it is not completely dissociated. As the solution is dilute, its molar concentration increases. Arrhenius attributed this increase in molar conductance to increase in degree of ionization, and he used this method as for calculating the degree of ionization of an electrolyte by the equation lambda m by lambda naught m. But according to the modern theory of strong electrolytes, the degree of ionization of strong electrolytes is unity even at moderate concentrations. Therefore, the above relationship is not correct in the case of strong electrolytes. Later, this concept was improved by Debye Huckle theory by considering the effects of inter-ionic forces in dilute solutions. Let us see the assumptions of Debye Huckle theory. All strong electrolytes are almost completely ionized at dilution. There is no uniform distribution of cations and anions in the electrolytic solution, but the orientation of ions is in such that one ion is surrounded by unlike charges or oppositely charges. Thus, each ion is surrounded by an ionic atmosphere of opposite charge. Solvent molecules are then attracted to this ionic atmosphere. In ionic atmosphere, the central ion is surrounded by a group of ions of opposite charge. In this figure shown, the central positive ion is surrounded by an atmosphere of negatively charged ions. Asymmetry effect. When an electric field is applied to the ionic atmosphere, the symmetry of the atmosphere about the ion is destroyed and the atmosphere becomes distorted. The ion experiences a retarding force which tends to drag it backwards. As a result, the movement of the ions is slowed down. This drag on the central ion is known as the asymmetry effect. The second factor which slows down the movement of the ions is the electrophoretic effect. In the solutions, the solvent molecules are also attached to the ionic atmosphere. When electric field is applied, the ionic atmosphere along with associated solvent molecules moves in the opposite direction to the movement of the central ions along with the associated solvent. Therefore, the central negative ion moving towards the anode has to move in the way the ionic atmosphere with its associated solvent molecules which is moving in the opposite direction. Therefore, retarding force on the movement of the ions arises due to the solvent molecules. Such an effect is known as the electrophoretic effect. The third factor which slows down the movement of the ions is the viscous effect. It arises from the viscous drag of the solvent on the movement of ions. The ion tend to move in the direction opposite to the applied electric field. This electrical force is opposed by the frictional viscous drag exerted by the solvent. For an ion with a given charge, size and shape, the greater is the viscosity of the solvent, the greater is the viscous drag, and hence smaller is the ionic mobility. Thank you.